So today what we want to do is finish up the discussion that we started aliasing. And I'd like to go through one more example of determining how a sinusoidal signal is going to alias. On Wednesday, we did all that analysis remaining in the continuous time domain. And what I'd like to do is take one of the examples that we did then and repeat it, but carry it out in the discrete time or digital frequency domain so we can see the parallel of how we can do those same computations there. After that, then I'll show you again how we might create a sampled version of a cosine or sinusoidal signal using MATLAB. And then we'll talk about the rest of the A to D conversion process. Last time we were talking about aliasing and how to prevent it. We'll go through the rest of the topics on how we do that and talk a little bit about quantization, and then with any time remaining, talk about some of the practical aspects of analog to digital converters, what their specifications are, what their different architectures are, when you choose one style over another, and the different trade-offs in your choice of an analog to digital converter. So with that, we're going to go back to a problem we solved last time. Again, we had solved the same one in the continuous time domain. Now we want to see how it appears if we were to try to solve the same problem in the discrete time or digital frequency domain. And the particular signal that we were looking at last time was a continuous time sinusoidal signal. That was a sine signal that had some phase with it. It happened to be a sine 2 pi times 100 t and had a minus pi over 3 phase on it. And we sampled that at a F sample that was 150 hertz. And recognizing that the signal itself had an analog frequency of 100 hertz, we found that this particular signal did alias, but let's see if we can come to the same conclusion and determination in the discrete time domain. And so if we ignored the fact that it could alias and just tried to determine directly what is the digital frequency that would result from sampling this signal with that particular sampling rate, we would have determined that that digital frequency was the original analog frequency normalized by the sampling frequency, or 100 over 150, or 2/3. And that's in units of cycles per sample. Okay, now if we needed to determine whether this is going to alias or not, when we did this in the continuous domain, we compared the analog frequency to half the sampling rate, which we call the Nyquist frequency. In the discrete time domain, what we're going to look at is that digital frequency greater than or equal to the digital equivalent of the Nyquist frequency, which is simply 1/2. Fs over 2 normalized by Fs would just give us 1/2. And so if we ask that question, in this case, yes, 2/3 is greater than 1/2, so therefore it will alias. And now we want to determine what digital frequency does it alias to. And if we take the discrete time version of our aliasing computation, we would start with the digital frequency, and then we subtract off integer multiples of the sampling rate. The sampling rate in discrete time is integer values. Sampling rate equals 1, 2 times the sampling rate equals 2. And so we want to subtract off is the nearest integer to the ratio of the analog frequency to the sampling rate, and multiply that by the sampling frequency in discrete time form. However, in this case, the discrete time equivalent of the sampling frequency is 1, and this ratio is nothing more than the digital frequency itself. So our alias frequency in discrete time frequency is just the computed digital frequency. That would be when we computed here without regard to whether there was aliasing or not, minus the nearest integer to that digital frequency. For our particular example, well, we had our digital frequency was 2/3, and we would want to take away the nearest integer to 2/3, which is just 1. So 2/3 minus 1 would give us a aliased frequency of minus 1/3. And when we reconstruct our aliased signal then, it's going to be our original x, our discrete time version now is going to be some x of n. If there was a magnitude out in front, we would include that, but there's only a magnitude of 1 here, so we won't have 1. We'll have a sine, and normally we would have a 2 pi n times our digital frequency, but in this case, we're going to use the aliased frequency added to whatever phase we had in our function. So for our particular example, that's a sine 2 pi n times the minus 1/3. And we keep our minus pi over 3 phase from the original problem. And once again, we don't like having negative frequency arguments in our sinusoid. So we'll write the equivalent version of this where I negate the angle argument. So now instead of minus 2/3 pi n, I'll make this a plus 2/3 pi n. Also change the sign of the phase. But now if I negate my angle argument, I'm going to have to put a negative out in front. As we showed last time, if we look at the sine and cosine projections of some angle, some plus theta and some minus theta, the sinusoidal projections are the ones along the vertical axis. The sine of a negative angle is the opposite of the sine of a positive angle, negative in the negative direction. So we need to include this extra minus sign. And we have the answer, which is the discrete time equivalent of the answer we came up with in continuous time in the last time we did this example. Then before we get back to lots of PowerPoint about the aliasing and all that, let's just detour a little and look at, again, how do we create these kind of discrete time sampled sinusoidal signals, whether they alias or not, using MATLAB. And it turns out the method is the same, whether the signal is going to alias or not. We don't need to know that ahead of time. We can just simply create a sampled signal by defining what are the sampling instances, when do the samples happen, and evaluating our original continuous time function at those particular times. So just as we described the way we convert a continuous time signal to a discrete time signal, we replace the time argument with integer multiples of the sampling interval n t sub s. In our MATLAB, we would want to replace this time argument only with discrete values, t sub s, 2t sub s, 3t sub s, and so on. If we wanted to, for example, take this signal for cosine 200 pi t minus 5 pi over 6 and sample it at 150 hertz, and let's look at the sample values that go from 0 to about 2 seconds. Well, we can certainly define the sampling rate, fs, as 150 samples per second. And the key is creating the time argument, the time array, that has the appropriate time values for when the samples are going to happen at this particular sampling rate. And probably the best way to do that is using MATLAB's incrementing array function, where you'd specify the start value, the end value, and what the increment is between values. In this case, we can use a precise increment that's exactly dictated by the sampling rate. The sampling interval is 1 over the sampling rate. And so by defining the sampling rate and then taking 1 over it, using it as the interval of this, we get the sample values the sample time values starting at t equals 0, then getting 1 over fs, 2 over fs, 3 over fs, and so on, resulting in 1 over t, or 1 times t sub s, 2 times t sub s, and so on. Then we simply evaluate this cosine function at all these different time arguments, and could use an expression such as this to do that. For cosine 200 times pi times t minus 5 times pi over 6. And again, MATLAB knows what pi is. It recognizes that and replaces that with the numeric value of pi. And this will evaluate and create an array x sub n that's the same size as our array of t values. and it will plug in those particular time instances into that function and give us the discrete time values for the sampled version of that signal. Now, this is a 100 hertz signal that we're sampling again at 150 hertz. Therefore, it is going to alias, but we didn't need to know that. This, just by evaluating this function at these particular instances of time, the actual sample values will have the aliasing in them. They will appear to be at a different frequency. If we wanted to do it at a different frequency, one that didn't alias, we could, for example, sample at 400 hertz for maybe a second and a half. The process would be the same. We would just define a different sampling rate and a new time interval, a new time array that uses the new sampling rate. And if we change the duration, we can change the end value as well. Let's evaluate our original mathematical expression at those new time instances, and we would get the new x sub n values at the new sampling rate. And this particular one would appear to have the correct digital frequency, which in this case, this is a 100 hertz signal sampled at 400 hertz. The discrete time signal would have a 100 over 400 or 1/4, 0.25 cycles per sample as its digital frequency. Let's pick up on our discussion about what do we do to make sure aliasing doesn't happen in our discrete time sampling systems. Last time we introduced the idea of including an anti-aliasing filter, an actual hardware low-pass filter in front of our A to D conversion hardware, so that even if our signal coming into our system had frequencies that could potentially alias, that filter would try to remove them so that after the sampling process, we didn't have any aliasing involved. Now, that is a wonderful concept. The challenge of doing this practically is that it's hard and expensive for me to make a really, really good analog low-pass filter that's going to pass through everything that we want to pass through and going to get rid of everything we want to get rid of. I have to make some practical compromises in the design of that filter. And so I will not be able to make a perfect one, which means there's still some potential for aliasing or signals that might alias getting into my system. And so we want to look at what else can we do to help that process to do a better job of preventing aliasing. If we don't want to put a super duper analog anti-aliasing filter in front of our sampling system, we could put a less expensive, less complex, lower order analog anti-aliasing filter into the mix and try to get rid of most of the signals that might alias. Won't be perfect. And typically what we'll do in that instance is use that kind of a simpler anti-aliasing filter in conjunction with some oversampling. Remember, oversampling means we're going to sample at a sampling rate that's higher than the Nyquist criterion says we absolutely need. And that oversampling could be by a factor of 2, 4, and maybe even up to 10 times what Nyquist says, just by virtue of how much signal we think might get through our filters that might alias and what our particular application is. For some less critical applications, we might not choose too much oversampling, but for critical applications like control systems, we might choose to use a considerable amount of oversampling just to make sure we don't get a lot of aliasing so that our control system's not chasing signals that aren't there, as well as making sure we have accurate representations of our original signals. And there actually is a way of doing this kind of oversampling assisted filtering and anti-aliasing that can be adjusted so that your entire digital system doesn't have to be operating at a very high sampling rate due to oversampling. And we'll talk through how that can work. First, we need to kind of reground ourselves again on how to look at these effects in both the analog frequency domain and the discrete time domain. Again, the relationship being that the digital frequency is normalized by the sampling rate. And so when we take samples of signals, we take their original baseband spectrum and make copies of it centered on every integer multiple of the sampling rate. in the analog domain. In the discrete domain, that means we're going to make copies centered on all integer values on 1, 2, 3, -1, -2, -3. If we choose a lower sampling rate, then the spectral copies, if we look at it on an analog frequency axis, which is what we've been doing, we shift down where our spectral copies occur. They still have the same widths to them, they're just closer together. Now, if we viewed this same difference between these same two in the discrete time domain, in the digital frequency domain, notice up here in the digital frequency domain, we have our triangles would cover maybe from -1/4 to +1/4. Whereas at the lower sampling rate, now they're going from -1/2 to +1/2. So not only are they closer together, but when we choose a lower sampling rate, it looks, if we look in the digital frequency domain, it looks like our spectrum has spread out a bit. Likewise, if we choose a higher sampling rate, we recognize in the continuous domain, that's just going to shift out further where these spectral copies happen. In this normalized realm of the digital frequency, though, what that looks like is that within a given range, the frequency spectra get narrower and narrower. And so we have this different appearance of different sampling rates depending on whether we're looking at the analog frequency axis or the digital frequency axis. And so if we look at this again from the standpoint of the digital frequency axis, when we have a baseband signal like this and we take samples of it and those samples repeat on every integer value of frequency, if we then choose a higher sampling rate, again, even though we do recognize that we're getting these spread further apart, they appear to spread further apart because they're getting narrower and narrower. In the opposite case, if we have a lower sampling rate, or sometimes we will do this operation called downsampling, where I have a bunch of samples already taken. I've gone through the sampling process, and for some reason I want to operate at a lower sampling rate. And downsampling is one way to get there. Downsampling, literally, as the name implies, says take all the samples you have, and you want to end up with fewer samples, which means they have to be spaced further apart. And the way we do it with downsampling is we literally throw away samples between the ones that we want to keep. So if I wanted to downsample a signal by a factor of 2, I would remove every other sample. Keep one, throw one away, keep one, throw one away, and so on. If I wanted to downsample by a factor of 3, meaning reduce the sampling rate by a factor of 3, I would keep one, throw away 2, keep one, throw away 2, and so on. Now what's happening in the frequency domain is obviously when we go from one sampling regime to another, we're changing the sampling rate. In this case, we'd be cutting it in half if we threw away every sample. In the analog frequency domain, we have our original signal and its negative version over here. And we've been making copies of that combination centered on every integer multiple of the original sampling frequency of our original signal, 1 over fs, 1 over, or fs, which is 1 over the time shift between these two samples. If I throw every other sample away, effectively I've doubled the sampling time, cut my sampling rate in half to a new sampling rate, we'll call it f data. On an analog continuous frequency kind of axis, we've dropped the sampling rate by a factor of 2, so the new sampling rate is equivalent to where the Nyquist frequency used to be. And now I can expect spectral copies of the waveform spectrum around every integer multiple of that one, just as if this was the original way that I had sampled the signal. And if we start off with a appropriate kind of signal and the right kind of sampling rates, in this case, this looks like it's actually worked out okay. In my new sampling rate, here's my new sampling rate. So we go to the new sampling rate over 2 to find its Nyquist rate. The original signal doesn't have any information above the Nyquist rate originally. This is just the spectral copy. And if we go through reconstruction and throw away everything outside of F data over 2, we're fine. However, downsampling can be a cause of aliasing if we use it indiscriminately. If the original signal before downsampling actually has information that goes all the way out to its original Nyquist rate, its original Fs over 2, then when I cut the sampling rate in half, we're going to make copies of that spectrum, again, centered now on the new F data, and a lot of it's going to alias, a lot of it's going to overlap. So the key to doing downsampling without creating aliasing is your original signal has to obey the Nyquist criterion, the criterion for the new data sampling rate, F data. So in this case, if I'm starting at this sampling rate and cutting it in half, my original data better not have any content above half the new sampling rate, which would be down here. And so all this that's above that is going to alias in when I do the downsampling. So that's why when downsampling is typically performed in discrete time systems, it's actually performed as what we call decimation, which is pre-filtering, low-pass filtering the sample data to the new Nyquist rate for the new data frequency, and then doing the sample throwaways to do the downsampling, so that if there was any signal that could have aliased, it won't be. All right. So why are we going through this? Well, we're gonna look at the case of oversampling as a way to help us for doing our analog to digital conversion without creating aliasing. We want to look at being able to use a lot of oversampling to make that work really well. But if we choose a sampling rate that's too high, that may not be a rate that I can sustain with the rest of my digital hardware downstream, in which case it may be necessary for me to downsample the data to bring it back to a sampling rate that's sustainable. In the simpler case, if we had a perfect anti-aliasing filter, this would be easy. But if we have imperfect and inexpensive and simple anti-aliasing filters, they might have a frequency response model like the one here that'll have a gain of 1, a magnitude response of 1 in the range of frequencies that we want to keep, and then slowly roll off to 0 for high frequencies beyond that. If I had a signal that was inherently just the baseband signal with no noise or no aliasing frequencies, that would be fine. Here we're showing a signal that has some content that we intend to have, that we want to keep, but this signal also picked up a whole bunch of noise at some much higher frequencies. And we don't want that noise to alias. So when we take this noisy signal and run it, if we could run it through an ideal low-pass filter, I wouldn't have to worry about it. We could cut out all the noise and none of it would alias. If I use a simpler anti-aliasing filter like the one shown here, we can predict that the output of the filter is going to be, well, the product of these two magnitude responses. So the anti-aliased signal coming into our sampler is going to still have some noise that eventually goes to 0, but because our filter didn't cut off very sharply, it's going to still let through a little bit of the noise. If we ignored that and just said, well, here's my original signal had this upper boundary in frequency, So let's sample it twice that to satisfy the Nyquist rate. That would put our sampling frequency here at twice Fn. And then when we sample it, we would get spectral copies of the original signal spectrum at every integer multiple of Fs. And down here in our range of frequencies that we're going to keep, we have a lot of aliasing going on from that noise signal that wasn't eliminated by the anti-aliasing filter. So that's not going to be satisfactory. This filter wasn't good enough to use just the basic Nyquist rate sampling for our original signal. If we could raise the sampling rate, however, so that this wasn't the Nyquist rate anymore, the edge of the original frequency content, but this point where the aliased signal is pretty much gone, then choosing that as our Nyquist rate, when we make the spectral copies, they're going to all end up at way out here at integer multiples of Fc, and nothing's going to alias anymore. And sorry, some of those are obscured, but in this case, by choosing a much higher sampling rate, we can prevent aliasing from happening. Now, our Nyquist frequency now is Fc, so we're going to keep everything in here. So we'll carry along our noisy signal, and maybe we'll get rid of that noise downstream as part of our digital processing. But the important thing is we haven't aliased anything and into the band of frequencies that we really care about. And so this is how we can use oversampling hand in hand with a less expensive, simpler anti-aliasing filter to do the job of preventing aliasing. So that's great. Why don't we just do that? Why don't we just choose a really, really super high sampling frequency all the time? That's going to minimize the probability of aliasing happening. It's going to make the job of designing an anti-aliasing filter simpler. Why not just choose a really high sampling rate all the time? And the answer is that particularly for cases where we're doing what we call real-time digital signal processing, meaning maybe I've got a sensor connected to my system and I'm getting samples every time, every sample instance, every 1/Fs. I'm getting a new sample. I need to do something with it, process it, decide if it's a problem or not, whatever my system's supposed to do, and spit out an answer. And I generally, in a real-time system, need to do that processing every time a new sample comes in. So I get a new sample, got to process it, put out an answer. Get a new sample in, process it, put out an answer. Which means the amount of time I have to do all my digital processing, all my digital filtering, all the computations that I'm going to do in my discrete time processing has to be finished from the time I get a sample till I get the time I get another sample. So basically that means my sampling interval T sub S is all the time I have to do all my digital processing. That's the upper boundary on the computation time I have to compute the answer before I need to go start over and do it all again. Therefore, the faster I make my sampling rate, the faster my digital processing hardware has to be in order to keep up with the samples coming in. The higher the sampling rate, the faster they're coming in, the less time I have to do my processing. What does higher speed mean? Usually means more expensive. I need faster digital hardware. I need faster analog to digital converters, faster digital to analog converters. Everything goes up in speed, and usually there's a proportionality between speed and cost. So the engineering of this sampling process is usually a trade-off between choosing a high enough sampling rate, certainly first to satisfy the Nyquist criterion, at least twice as much as the highest frequency we want to preserve in our signal, plus some amount of oversampling to minimize the possibility of aliasing, working in conjunction with an anti-aliasing filter, hopefully an affordable one, that can get rid of and can be used in conjunction with the sampling rate, the oversampling, to prevent any signals that might alias from getting into my system. There's one more little trick in our handbag that we can sometimes pull out, excuse me, If I need to use oversampling a lot to prevent aliasing to the point where the sampling rate I end up with is way too high for the rest of my downstream processing system, we can do some of the job in the digital domain as well as the analog domain. And here's how that setup works. We use a simple low-order anti-aliasing low-pass filter in analog form, do our high-speed sampling, so we buy a faster analog to digital converter with enough oversampling to work in conjunction with that inexpensive anti-aliasing filter to give us a very clean signal with no aliasing. But if that sampling rate's too fast for the rest of the system, what we can do is actually use some digital filter, some high-speed digital filtering, sometimes built into the A to D converter, to further reduce any alias signal that's in that original signal that came in, and then go through that downsampling process, restoring the signal still to a discrete time signal, but at a lower sampling rate, one that the rest of my system downstream is able to keep up with. And part of the job of this extra anti-aliasing filter will also be the decimation filter. We need to make sure that the downsampling process doesn't create aliasing as well. So how does this all work? Well, again, we start with our noisy signal with the band that we want to keep and a slow roll-off anti-aliasing filter. So when we run this signal through that filter, we still got the same original analog filter, analog signal that we're trying to digitize. But now I'm going to choose a very high sampling rate. And in some cases, we can get away without quite as high a sampling rate as we might have needed if we're okay with some of the noise part of the spectrum aliasing, overlapping. We don't want that signal anyway. And what we'll do is take that next stage. So we have our discrete time signal with all its spectral copies and some aliasing going on, but aliasing only going on in the range of frequencies that we don't care about, the noise part. We don't let any aliasing happen in the original span of frequencies we wanted to keep. And then we put a very good low-pass digital filter after that sampler with much sharper cutoff, much more ideal, and use that to get rid of all this stuff that aliased and all that was originally noise anyway. So we're left with a cleaned up signal that we can then downsample back to a sampling rate that the rest of our downstream hardware can keep up with without stressing so much. And this extra digital filtering both prevents aliasing from getting through from the original signal and any aliasing that might happen in the downsampling process. And so we end up with a clean anti-aliased signal at a sampling rate that the rest of our hardware can work with, can deal with. That enables us to use fairly slow order, slow roll off anti-aliasing hardware filters, and we try to put in some much better fast processing, high order digital filters to do a much sharper cutoff to get rid of the noise and alias signal. So our choices are make a better anti-aliasing filter and not need to use quite so much oversampling, or use a lower order filter, use some degree of oversampling to accommodate that, to give yourself a little bit of headroom. And if this oversampled rate is too fast for the rest of the system, we can clean it up some more with a digital filter and downsample to a more reasonable rate. Okay. So those are some of the practical approaches that are used to manage the fact that we have signals that might alias. We don't want that happening. If we look at the whole front-end analog to digital conversion process again, we can break this up into a couple of stages. And let's look at what the signals look like before and after each of these stages. Let's say we have a raw signal coming into our system that we're going to digitize, and maybe it's got some pretty high frequency noise on it. Once we roll through that anti-aliasing filter, it's a low pass filter, so it's going to remove high frequencies. It's going to smooth out that signal somewhat. Hopefully it's removed most of what's going to alias. Now, practically, an analog to digital converter that's going to now take that signal and digitize it, we can break that up into a couple of different actual operations that have to go inside that device. The first of which usually is some sort of sample and hold circuit, meaning we're going to have to grab the signal value, the sample value from our original signal, so it's varying in time, but my A to D converter cannot work instantaneously. It's got to go through some processing in order to figure out, okay, what output value should I create for this particular input voltage? And while it's figuring that out, it needs something to hold that voltage constant for it so it can go through its tests and figure out what to put out. And so that's what the job of a sample and hold is. We grab a sample at some instant in time in our waveform, and while the waveform is changing, we're going to hold the output of this sample and hold constant so that the A to D converter hardware can work on figuring out what level is that. And then when it's done, we'll grab a new sample and hold that till the next sample time. And then grab a new sample, hold that for a certain instant of time. So usually we have to precede the whole process with a sample and hold operation, which has its own spectral impacts. And if you read through the textbook material, it turns out that it's not going to change the fact that we're going to make spectral copies of our original signal when we sample it. It's just going to change how big some of those copies are. They're going to start tailing off in magnitude as we go further and further out. An effect that we don't necessarily have to worry about modeling for our understanding the sampling system. So we're going to simplify that and assume that doesn't have a great effect on the spectral content. There's another step, though, that after the signal's being held, we have to actually, through some mechanism, figure out how to convert the voltage level of our input signal that's being held to a binary number of some kind of digital signal. And that's the process that how you do that depends on the style and architecture of the A to D converter that you're using. So it's, again, that we can break up into a couple of processes. First, we have our sampling process, which is usually carried out by the sample and hold circuit. We recognize that part of what's going to go on in that conversion of voltage level to digital output is actually a quantization operation. It's going to be some rounding involved. We're going to turn a continuously varying voltage into one that has certain staircase, discrete level that we can depict with our finite number of bits in a digital signal. That being a quantization process means there's going to be some error, some difference between the signal I bring in and how I'm representing it with a digital signal. And there's some range of input voltages, all that result in the same digital output. So if my original signal was closer to this level, well, I've got still a little bit of error between the one I put out and what I've actually have. That difference between these quantized values of outputs that I can depict, can describe with my digital output compared to the actual continuous input that we have is what we call quantization noise or quantization error noise. So when we look at an A to D converter, there's a number of specifications things that we need to look at, what its performance is, things that define its operation. And the first big decision to make when buying or choosing an A to D converter is how many bits do I want in my digital output? We'll call that B. That then immediately determines how many different levels can we resolve with our A to D conversion output. How many different binary codes do we get out of this circuit? In that case, the number of different quantization levels is 2 raised to the power of the number of bits. So if I have an 8-bit converter, I get 2 to the 8th or 256 different counts that can come out of my A to D conversion process. The other thing that we keep track of is what's the input range, sometimes called the full scale range. That's what range of analog inputs does my A to D converter convert into a varying output signal. There's some maximum voltage and some minimum voltage between which the A to D converter will give you a proportional digital number, a number proportional to the voltage in the device. If I choose to put in a voltage that's above the Vmax, the upper end of the full scale range, I can't change my digital output. I can't make it any bigger than the maximum value. So effectively, usually my A to D converter will just give you the top value for any voltage that exceeds the upper range. And so we get some clipping in the output of the A to D converter. We can't go above the maximum, and so if our input exceeds it, we won't see that. Likewise, the same at the other end. If we put in a voltage less than Vmin, then the A to D converter can't put anything out lower than its lowest number, and it will not give you anything that's distinguishable for that lower value. It'll just say, nope, it's just the maximum low, that code. This clipping is actually a very nonlinear phenomena that's hard to model and predict, and it's definitely something that we want to avoid. And so we need to choose carefully the full scale range of the A to D converter and match it to the actual excursion range of our input signal. We don't want our input signal exceeding that, or else anything that exceeds it one side or the other, we won't digitize that. It'll just give us the max values or the min values. A to D converters also vary in whether this full scale range is all positive or bipolar, positive and negative. And depending on its power supply source, that full range could go from 0 to 5 volts, 0 to 3.3 volts, plus or minus 12 volts, plus or minus 5 volts, depending on how the device is designed and how we connect it up. The resolution of an A to D converter is how big of a voltage is each little step here in binary output representing. And we get that number by taking the full scale range in volts. What's the maximum range of signals we can convert, and divide it by the number of levels, which is 2 to the B. And this would give us then volts per A to D count. The maximum quantization error then, if this whole range of input voltages give me the same digital output, then the maximum error could be half of one of these steps, or if one of these steps has a distance of delta, then delta over 2 is the maximum error in my quantization operation. So two fundamental things that we need to decide when we choose an A to D converter. How many bits is it, and how fast is it? How we answer those two questions will determine what A to D converters I can use and what style, what internal architecture will work to meet my needs. The speed is dependent on what sampling rate we need to sustain. The number of bits, well, it turns out the number of bits is related to the signal to noise ratio I need in my system. This quantization error we can model as a statistical noise, and if you do, you can show that the signal to noise ratio of an A to D conversion process is directly related to the number of bits. because the number of bits changes the number of quantization levels and how close together they are. And since the maximum quantization error is plus or minus a delta, delta over 2, the wider the delta is, the bigger that is, because of, well, the larger delta is due to the number of steps you get, which is related to the number of bits. The more error you're going to have, the more quantization error and quantization noise you're going to generate. And so this is the relationship, that kind of the rule of thumb that's been developed, that if you have a certain signal to noise ratio that you're trying to maintain in your system, your quantization signal to noise has to be that good or better. And the quantization signal to noise ratio is directly related to the number of bits. It's basically 6 times the number of bits plus 2 dB or so. So if I have an 8-bit A to D converter, then I can make a system and sustain a signal to noise ratio that's 8 times 6 or 48 dB plus another 2, roughly 50 dB of signal to noise ratio. If I need more than that, I need more bits. And for every bit I add, I get 6 more dB of SNR. Now, the analysis that underlies this has a couple of assumptions, including that you're using pretty much this whole full-scale range with your signal. If you've designed your A to D and the front end preamplifiers and filters and everything so that you're only using a little part of this range, then you're not going to get this signal to noise ratio because you don't have much signal. Likewise, if you aren't careful and you have signals that go too big and go outside the range, well, you're going to have clipping, and that's a whole nother problem. But roughly, this is the rule of thumb. You need about 6 times the number of bits will give you the plus 2 dB, would give you the SNR in decibels that you can sustain with a particular A to D converter. A to Ds also have a number of other specifications. One that you might see is no missing codes and monotonic transfer function. Monotonicity implies that if you put an increasing voltage in, you're always going to get an increasing digital number out. If you started here and had a slightly higher analog input voltage and it gave you a lower digital output, that's non-monotonic. It turned around. It wasn't supposed to do that. Pretty much all modern day A to Ds are of such good quality that monotonicity is usually not a problem. Missing codes is the idea of if I take there is an actual binary code that doesn't come out. I just kind of skip that one on the way up the ladder. And again, most modern devices will say right in their specification, no missing codes. These problems are generally due to manufacturing defects. We're out of time, so I'll refer you to the notes here that give you a pretty good rundown on the different architectures for internal architectures for A to D converters and the clever ways that they take a voltage and determine what is a proportional digital or binary number that goes with that voltage. We have ramp converters. We have successive approximation converters, which are probably the most popular intermediate speed A to D converters. And in fact, here's an example of one, give you an idea how good these are. You can get a 16-bit A to D converter that runs at 4 mega samples per second. That's 4 million samples a second, 4 megahertz at 16-bit resolution. That's pretty amazing. If you need tens or hundreds of megahertz of sampling frequency for really high speed work, then you only have one choice. That's a flash converter. Flash converters are very expensive, generate a lot, use a lot of power, generate a lot of heat because they are literally a bunch of comparators. And every time you add a bit to the resolution of a flash converter, you have to double the number of comparators in it. So these are ones that are extremely fast, but also extremely expensive and hard to make in very high resolution. So these will typically be maybe 8-bit kind of conversions, or possibly 10 bits if for really expensive ones. And people have dreamed up a number of different hybrids that are kind of partially flash with some sequence processing to make some intermediate speed ones. So there's a number of different architectures. Another popular one for lower speed conversion are delta sigma A to D converters, often used in audio. These can be very inexpensive A to D converters with very high precision. They just can't go very fast. So as an example, here's a delta sigma 24-bit resolution, which is incredible, but its top speed is 4.8 kilohertz for a sampling rate. So there's always this trade-off between speed and resolution and cost. It's a three-way balancing act. And depending on what you need for resolution and what you need for speed, there's a different flavor of A to D converter that's suited to your application.